In my early career from 1983, when I was a first-year graduate student, until the year 2000, this is almost 17 years, I was completely engaged in transmission electron microscopy. And I was studying the deep physics in transmission electron microscopy and also uses of materials research. Once I ventured ahead, situation changes. By 1995, I was the first year at Georgia Tech as associate professor. I was in charge of the electron microscopy facility. And when I get there, I realized my startup funding was not enough for get a new microscope, because get a new microscope cost about $1.5 million that time. My startup was only $300,000, so it was not enough at all. So I was thinking, well, can we use electron microscope for something different? Just instead of imaging and structure analysis. So that time we started to use a very old microscope, which was that time was around 35-year-old microscope, very old. But we be able to open up, modify, and we put that time was the carbon nanotube sample in the TEM. So when we look at that, we find that nanotube was wobbling under the electron beam. And then we had the idea, so can we make it to resonance if we apply oscillating voltage? So we did, and then we published a paper in the Science, and was the first paper on nanomechanics. Use transmission electron microscopy to correlate what you see with what you measured. That's the first one. So that was 1997, 98. So when I proceed, there's only so many different time nanotube I can measure. What's next? So I started thinking I should make a nanomaterial myself. This is year 1999. What material to make? You can make, or somebody already made carbon materials, silicon-based materials, but not oxide. So I started making oxides. We were the first few groups to make oxide nanostructures and published the first paper on nanobelts in 2001. Then we used transmission microscopy to study it for structure analysis. Until 2003, I said, well, just look at it is not enough. Can we make measurements like electrical, optical properties? So we did. After that, we said, can we measure the piezoelectric coefficient? That's another property of this nanostructure. Finally, we realized we were not very good measure the piezoelectric coefficient, but my idea would change. Let's say we use this for energy conversion to mechanical energy to electric power. That was 2005, 20 years ago. So what do we call this? We call nanogenerator. So since then, for now, 20 years, we have been staying in the same field, major field, ever since. That's started my career in energy, electronics, as well as sensing technology. So this transformation was a long transformation, was not an abrupt transformation. I would say called evolution, slowly evolve, rather than abrupt change, because you never know if you do these things how far you can go, how long you can go. But up to now, we work on the energy field, become one of the important energy technology for the global development, which I'm very happy to see. Also, it was what I expected 20 years ago. So this is my story, how I come from electron microscopy to energy-related research. Yeah. When we first started the work, in the very first paper I wrote we want to convert a mechanical energy in biological system, such as your body motion, your finger motion, your muscle stretching, even include blood flowing into electric power, so we can make medical devices self-powered. So that was the first paper, self-powering appear. Twice in the paper, self-powered is at the end too. So the technology we invented was targeted for biological system at the very beginning, because biological system is a slow, low amplitude, irregular motion. Can we utilize such energy for medical purposes? So that was the initial idea. Two effects. One is a piezoelectric effect. Basically, one material which has piezoelectricity. If you have body motion, this is piezoelectric materials will be bending or stressing, which generate a polarization across the thickness. So you see a voltage. And this voltage will drive the electron flow in the external load back and forth. So this is the piezoelectric effect. The second effect is triboelectric effect, which uses the contact of two materials, more general. You don't have to be piezoelectric material. Two materials in a physical contact that make the charge. If you separate them apart, they generate voltage, and this voltage drive the electron flow back and forth in the external load. So we demonstrate the piezoelectric effect 2006. We demonstrate the triboelectric effect 2012. And these two have become the important technology for medical research, because it has the advantage of operation at a lower frequency. That means a very slow motion. The second one is low amplitude motion. It's something gentle, which is a typical thing with biological. So ever since we published the first paper in 2006, our target was to make for example, like a pacemaker self-powered. We wrote the first paper 2009, used piezoelectric effect for use heart beating for power generation. It was the very first paper that time. And after 11 years, 2019, Professor Zhou Li and myself, we made the first self-powered pacemaker, the first time in the world. So it was a long journey, but apply our technology in biology system was the initial mission. We're going to change the medical research in a few aspects. Number one, medical sensing. This includes the in vivo and in vitro. In vivo, we talk about implantable medical device, such as a pacemaker, such as the internal body sensing system, as well as brain stimulation system. This is, we can provide it as a power source for those devices. So you can make a pacemaker last a very long time without changing the battery. So that was the first one, in vivo. In vitro, it has a lot of applications outside body. First one, for wearable electronics. Anything help us to detect biological signal changes, drive the drug infiltration to the skins, as well as sensors for, I would say, like biofluid, as well as sensors for motion related, sleeping behavior, sports, physical characteristics in sports, heart beating. Also, you can measure things like your physiological signal change during a specific external excitation. So all this one can be done by in vitro. Also for healthcare. For example, for elder people, their walking behavior, the way they sit there. If I sit here, cannot get up, how do the other people know? Especially in the home, right? So in that case, you have to build the sensors on the chair. So if I can't get up, there was a signal tell I'm fine. If not, you can call the nurse for that. So all this is related to elder people care. That which have a great market in the future. So many things say, one word, in the biology, as long as you can move, we can convert that motion action into electric signal, which is a sensor signal, and apply this to anything you can think about. For the future challenge to humankind, there are several fundamental things. Number one is the energy challenge. The second one, health. These are the two things many of us care about that, especially about health. People want to live longer, healthier, and happier. So in the past, we have many journals on medical science, but we want to expand that to the medical science related to our current research in the society in the broad. So we want to serve the people in the materials community who have a biological application or medical application. We also want to serve the people, for medical people, they have a need for materials. We also want to serve the people who want to build a medical system, so this thing can function, can detect the species or signals you wish. So I think there was a great need for medical materials, but of course we cover a lot more than just materials. So I think there's a need for that, because health is one of the fundamental challenges to humankind. The Medmat is not limited by the name. We include medical materials, biological materials, materials for implantable medical devices, sensors, bioelectronics, also involve the integration of the different sensors for medical purposes. Also build a device use nanomaterials. So we come from materials to devices and to system integration. Something that give you a package you'll be able to use. So therefore, we are not only by the name. And so the readership can be from materials community, biological community, medical community, even electronics community. So it's broad. We do not limit this our scope. We want to say anything related to medical will be interesting for this journal. First of all, we welcome our readers, our authors submit superior quality manuscript to Medmat. We want to make this journal to be a flagship journal in the field. We will do our best to make sure the processing, review, and the publication process fast. I had served as chief editor for Nano Energy for 13 years. I know that one of the key for success is faster, faster, and faster. Especially in today's society, people want to be review fast, process fast, publish fast. They cannot wait. So therefore, we not only want to be fast, but also warranty the high quality of the journal, so it can be published excellent papers which serve the community over long-term run. So first, please submit your great papers to us. I will make sure your paper will be properly promoted, as well as we will raise the impact to many different areas as it's published. So we want to make this a flagship journal over long term.